the singleton pattern ensures that a class has only one instance. It sounds like it requires special machinery, a getInstance method, a private constructor, a static property to hold the instance. In many languages, it does. In Node.js, the module system makes this almost trivially easy. When you require a module, Node.js executes that file and caches the result. Every subsequent require of the same module returns the cached result, the same object reference, not a copy, not a new instance. So the classic singleton in Node.js is this: create your object or class instance inside a module, assign it to module.exports, and you're done. Every module that requires it gets the same instance. There's no special pattern to implement. The module cache is the singleton mechanism. This explains a common pattern you see in Node.js codebases, a database connection module that exports a connected database client. That file connects once, exports the client, and every other module that imports it gets the same live connection. One connection, shared everywhere. That's a singleton. But here's where Node.js has a surprising gotcha. Module caching is per package version, not per application. If your application depends on two packages, call them package A and package B, and both depend on version 1.0 and version 2.0 of the same shared module, Node.js will actually load that shared module twice. You get two instances. Two singletons. This matters for things like configuration, event emitters, and shared state. The assumption that this module exports a singleton holds only when you have one version of it in your dependency tree. The moment you have duplicate versions, which NPM happily allows, you have multiple instances with no warning. Understanding this limitation is essential before you lean heavily on module-based singletons. Let's make the duplicate singleton problem concrete, because it's responsible for some of the most confusing bugs in the Node.js ecosystem. You're building a plugin system. Your core module exports a plugin registry, a singleton that other modules register plugins into and query plugins from. You use module.exports equals new plugin registry in the core module. Beautiful. You install two third-party plugins. Each one was developed against a different version of your core module. NPM installs both versions. Now you have two plugin registries in memory. Plugin A registers into registry version 1. Plugin B registers into registry version 2. Your application queries registry version 1. Plugin B is invisible. The bug is silent, confusing, and completely non-obvious from the application code. This is not a hypothetical. It happens with logging libraries, event bus implementations, configuration managers, any module that relies on shared singleton state. The book notes several strategies for dealing with this. One is to use peer dependencies rather than direct dependencies, which forces NPM to use a single shared version. Another is to explicitly check the global object, attaching the singleton to global.myapp.registry instead of relying on the module cache. A third is to architect your system to not rely on singletons for cross-cutting concerns. The important lesson, in Node.js, a singleton really means a singleton per resolved module path in the current process. When that path is unique, one version, one location, it behaves as expected. When there are multiple locations, multiple versions, the assumption breaks. Knowing this doesn't mean you should avoid singletons. It means you should be intentional about where and how you use them. Once you understand singletons, the next question is, how do modules share their dependencies? How does the database layer get the database connection? How does the service layer get the logger? This is the wiring problem. There are two main approaches, and they represent very different philosophies. The first approach is singleton dependencies. Your database module exports a single connected client. Any module that needs the database simply requires that module. The require is the wiring. It's simple, it's direct, and it works well for most applications. The downside is tight coupling. Any module that requires the database directly is permanently bound to that specific module. The second approach is dependency injection. Instead of requiring dependencies directly, you accept them as parameters. A constructor, a factory function, or a configuration object receives the dependencies explicitly. The module doesn't decide which database to use, it receives whichever one its caller provides. The book illustrates this with a concrete comparison. Without DI, the service layer requires the database module directly. Testing requires mocking the module, which involves intercepting require calls, messy. With DI, the service is a constructor that accepts a database parameter. Testing passes a mock database object. No module interception needed. Dependency injection makes two things dramatically easier: testing, pass a mock, and reconfiguration, pass a different implementation. The trade-off is that someone needs to wire everything together to know which database instance to pass to which service. This wiring code often lives in a composition root, the entry point of the application. Most Node.js codebases use a mix of both approaches. Module-based singletons for stable infrastructure. Dependency injection for business logic that needs to be testable. The dependency injection approach raises an immediate practical question: if modules don't require their own dependencies, who wires everything together? The answer is the composition root. A composition root is the single place in an application where all the dependencies are created and connected. For a web server, it's typically the main application startup file, the index.js or app.js that Node.js runs directly. This file creates the database connection, creates the logger, creates the configuration, and passes each to the constructors or factories that need them. The services themselves know nothing about how they were wired. They receive their dependencies as parameters. They work with whatever they receive. The composition root is the one place with full knowledge of the application's dependency graph. This pattern scales well. As the application grows, the composition root grows with it, but all the complexity of wiring stays in one place. Business logic modules stay clean and testable. You can change the entire database backend by swapping one object in the composition root, without touching any service code. For larger applications, dependency injection containers, libraries that automate the wiring, are common. Awilix is a popular one in the Node.js ecosystem. You register dependencies into the container with names, and the container automatically injects them based on constructor parameter names or explicit configuration. The container becomes the composition root. But for most Node.js projects, explicit wiring in a startup file is clear, debuggable, and sufficient. The book recommends understanding manual wiring first before reaching for a container. The choice between module-based singletons and full dependency injection is a spectrum. Know both. Apply each where it fits.